Hi, everyone. Welcome to episode 4 of Verifiably Random. My name is Min,
And I'm Mark.
And I'm John.
and we're here to bring to you a fantastic episode about quantum computing. It feels a little bit futuristic, I will say, to talk about quantum computing, but we're going to learn a lot about the basics of quantum computing, talk a little bit about how blockchain has played into it, and then give you a little bit of insights into what's been happening on Algorand, but other places as well. So I'm excited. I'm excited for this episode. Maybe to kick it off, let's get right into the basics of quantum computing. I think I know very little. I've heard a lot of terms being thrown around: hardness, trap door. John, tell us what they are.
I mean, we are living in the future. The year 2000 was 24 years ago. When Gateway used to sell computers, they used to call it Gateway 2000. They thought that would last for a long time. It was 24 years ago. Quantum. I mean, what is it? It's in a nutshell. Of course, quantum mechanics comes from the world of physics, how we describe the universe. At first, we thought gravity worked, as Newton described it, i.e., mass attracts each other. And then after a while, we built the Large Hadron Collider and other things, and we figured out, what, maybe there's this theory that our world is made up of these, quantum fluctuations or whatever. And so this is, something you'd need a PhD in physics to understand. But it turns out that we can harness, I suppose, as we do in life, we can harness some of these physical properties of the universe to achieve interesting results. And so let's talk about what is a computer. A computer is a digital device that uses electricity. It uses electricity. If, for example, something is 5 volts, it's a 1. If it's 0 volts, it's a 0. I'm kind of simplifying that, but that's essentially how computers work. Computers represent data as these ones and zeros using electricity, and they operate quite quickly, and they can solve problems, obviously, and they've been a revolution. So quantum computers are just another type of computer, except they process information a little bit differently. And so they are interesting because they can solve certain kinds of problems really quickly. But I want people to understand, this is not like, years ago when your friend had a graphics card or a GPU and he could play, I don't know, Tomb Raider or something on better graphic settings than you could. This is not like a general purpose thing you're going to add to your computer at home. Quantum computers are very specific computers that do very specific tasks. They're not general purpose computers.
And they use qubits rather than bits, right? And bits can be, if my understanding is correct, bits are binary, it's 0 and 1. Qubits
Right.
can have many more states to them, right? Isn't that is that the core of like what makes them so powerful and makes them so different?
It is indeed. And so you got to think of it this way. When you're calculating things on a normal computer, everything is deterministically or definitely a 1 or a 0. And by the way, if a voltage is kind of somewhere between 5 and 0, maybe it's like 3.7, the computer will interpret that as one or the other. So everything is a definite 1 or 0. And so this is fine, but it means things happen quite sequentially. In quantum computers, we use, as you quite rightly said, Mark, qubits. And in the case of quantum computers that attack cryptography, we have to use error-correcting qubits, which we can talk about a little bit later. But those qubits, as you say, are both a 1 and a 0 at the same time with a certain probability. And for those of you who are familiar with uncertainty principle and quantum entanglement and superposition, a qubit is indeed maybe 30% a 1 and 70% a 0. Or maybe it's 50% a 1 and 50% a 0. And so the whole process of running a quantum calculation to attack cryptography is the process of passing qubits through quantum gates in order to change their probability in such a way that when you finally read the probability across all of the qubits, you collapse the quantum waveform and you get the answer. A lot of mathematics in there, but it's basically pretty cool science.
And the size of the size of a quantum computer is expressed by the number of qubits it supports, right? Is that right?
Yeah, that's my understanding. Absolutely. So normally, we would talk about normal computers. We would talk about kind of sure the bit width of the CPU and the kind of data types it can manipulate. But we'd also talk about the clock speed of the computer and things like that. In a quantum computer, yeah, it tends to be, as I understand it, based on the width of the qubits that you can perform quantum computations on.
But then we also have to be realistic about where we are. In other words, there is not a single quantum computer that exists that does practical algorithms today, right?
Well, I mean, yeah, you're not going to find one down in Costco, but the NSA probably have one, Mossad probably have one. You know how these organizations operate.
Are these, and then like physically, am I like, I'm imagining these like IBM giant rooms with just giant computers, but that's back in the 60s and the 50s. This is different, isn't it?
Yeah, I mean, physically they look like a chandelier. They're usually like
Oh,
kind of like this. They kind of taper in. They
okay.
hang from a ceiling, and they are. I actually have no idea what's inside, but they get very cold. They're usually like minus 230 Celsius or so.
And they're not good for everything, right? It's like you wouldn't use a quantum computer to do like a regular calculation.
Right.
They would only be good for certain particular use cases, right? And then, is that right?
Yeah, absolutely. And so there's kind of like, on your normal computer, you can run loads of apps. You got like from Excel all the way to WhatsApp, right? On a quantum computer, we don't run apps in that traditional sense. They don't have a traditional operating system that you start applications on. Instead, they run algorithms. And there's only kind of, I mean, there's more than two, but there's two prominent algorithms that people are afraid of. Shor's algorithm, named after Peter Shor, and Grover's algorithm, named after something Grover. I forget I forget his first name. But ultimately, Shor's algorithm is very good at integer factorization, and that kind of breaks elliptic curve cryptography that we use for Bitcoin, Algorand, Monero, etc. And it's very good at breaking RSA. Grover's algorithm, on the other hand, attacks symmetric cryptography, so AES, ChaCha, and it also can attack hash functions and other search-based problems. And so these are the two tasks it does well. It factors numbers and it searches quite quickly. I mean, roughly.
And John, do any of them break the trapdoor that I keep hearing about? What is this trapdoor thing? Sorry, I'm coming back to, I need to know.
Yeah, I mean, I thought I was going to be the science guy. Yeah, but yeah, you're right. The trapdoor function. So at the heart of all crypto systems is the idea of a trapdoor. And let's talk about that for a moment. I mean, the whole idea is that it's easy to encrypt something. It has to be. Otherwise, if you have to wait thousands of hours to encrypt something, not going to be very useful. But it has to be hard to decrypt without the key. And that's the idea of the trapdoor. Easy one way, hard the other. You can go into the trap easy, but you're not coming out of the trap without the key or the password. That's the whole idea of a trapdoor function. Now, in traditional crypto systems, these trapdoor functions, people sit around and they think of mathematical structures that can create trapdoors. And I think there's one that I really like explaining because it's super easy. Because elliptic curves are quite hard. It's all like algebraic structures and stuff. RSA was the first public key crypto system. It was the first cryptographic system that had a public key and a private key. And RSA's trapdoor is really easy to understand. RSA bases its trapdoor function, and I think, Marc, we talked about this the first time we met for breakfast. It bases its trapdoor function on the idea that it's easy to multiply two prime numbers together. 3 and 7, very easy to multiply 3 and 7, you get 21. But it's hard to factor two prime numbers which multiply together you get a semi-prime. It's hard to factor semi-primes. And why is that? It's hard to factor a semi-prime because there's only 4 factors to a semi-prime. Itself and 1, in this case 1 and 21, and also the two prime factors that created it, in this case 3 and 7. Now, of course, with 21, we can figure it out in our heads. But if I gave you a very large semi-prime, i.e. a number with like 100 digits in it, and I said, hey, this number is 100 digits long, it ends in the number 3, what are the two prime factors that I multiplied together to get this? You would be doing long division all day long to figure that out. And it turns out, if we make that number big enough, it's hard for classical computers or regular computers too. And that's a trapdoor function. That's an example of something easy one way, easy to multiply, hard to factor.
I remember that breakfast. It was a very geeky breakfast.
It was a geeky breakfast, but great bacon. Yeah.
So if you now put this in the context of a blockchain, right? Everything is cryptography based. So talk to us a little bit about the risks that quantum computers have with regards to blockchains.
Sure. So, so as I mentioned earlier, quantum computers use qubits, or as you mentioned, they use qubits. They can run these algorithms. Let's concentrate on Shor's algorithm because it's the one that really breaks Bitcoin and breaks cryptocurrencies. And by the way, breaks the cryptography we use for the general internet. Forget about cryptocurrencies.
Could potentially break Bitcoin. Hasn't broken. Could potentially break Bitcoin.
Right, could potentially. Sorry, I should say could potentially because these things don't exist yet in public. You're absolutely right. Don't want to create alarm. And so, you got to look at where in cryptocurrency, specifically, for example, Algorand, Bitcoin, and others, where do we use these trapdoor functions that are predicated upon the elliptic curve discrete logarithm problem, which is like factoring integers in like over prime field. So where do we have this hardness that quantum computers can just smash like a piece of glass? And the answer is kind of three places. One, in the linking between the blocks. So blocks are kind of linked with hashes and signatures and other things like that. So we use cryptography linking the blocks. We also use cryptography when you're spending.
That's the history, right? That's basically, right.
Yeah. That's the history of the chain. Exactly that. Yeah. We also use it in accounts, right? When we're spending cryptocurrency, we digitally sign a transaction. So it's used there in that digital signature. And then finally, can you think of the last place where it's used?
I think consensus, no?
Yeah, consensus. So in consensus, we have the VRF. The VRF is predicated upon the hardness of elliptic curves again. And so there, the act of doing the consensus thing in Algorand and in other cryptocurrencies uses this hardness as well. So quantum computers can come in and they can specifically attack these things, the VRF, digital signatures, etc. And so, to answer the question, where does the quantum problem hit for cryptocurrency? The answer is around these things, which are cornerstones of how the system is built. Now, normal computers can't attack these things. It's just too hard for them. But quantum computers, especially those that have enough qubits to run the Shor's algorithm, which is a very targeted algorithm for breaking modern cryptography, they can attack these things and they can break them. So what would that mean? It would mean that someone could forge your private key. Someone could add a bad block to the chain, and someone could go back in history and swap out one of the transactions. These are the kind of things you can do with a quantum computer. I'm kind of simplifying this a little bit, but that's essentially the concern.
I was reading this report by Deloitte that was saying like 65% of all ether are vulnerable to quantum attacks. And I think it's, they sort of split it up in terms of, they call it like storage attacks, right? Basically like any public address that has been exposed on the blockchain, which happens every time you send something, if there's a transaction. And this idea that you guys keep going back to that, hey, but this is in the future. It's not, there are no quantum computers now, but in sort of thinking about security against quantum computing, it is about that, like a lot of times you can store that content, right? And then you can attack it when and if these quantum computers are around.
Right, exactly that. And so, Vitalik is clearly very gifted and more intelligent than I am. But at the end of the day, I looked at his quantum plan and to me, it didn't resonate. The general thesis around the Ethereum leadership is that, hey, a lot of Ethereum is predicated around the security of hash functions. Hash functions are only reduced to the square of their bit strength. And so they're still 256-bit hash functions are still 128-bit strong. That's pretty good. If we have a problem, we can kind of sort things out by rolling things back or by shifting to hash-based accounts or other things like that. I think that that's not a great solution. I would rather tackle this stuff head on. I think it's better to have an elegant transition to a post-quantum era, okay, where we do change or do protect the history of the chain,
right?
The consensus mechanism, the signature scheme, without waiting for someone to come in and attack us first. But the problem is people don't want to do this because it's hard. This stuff it's hard mathematically, it's hard to code, it's hard to test. And in some cases, we don't even know if indeed these algorithms are definitely quantum secure because it's an emerging area of science and mathematics, etc.
And so how do we think about this concretely from an Algorand perspective? I mean, we claim to be quantum secure, right? So talk to us a little bit more about that. Does it mean we cover all the aspects of quantum security, the three aspects you covered? It only covers one of them, right?
Right. So maybe quickly what I'll do is I'll just describe very briefly how we can build trapdoor functions that are quantum resistant or quantum secure. And so, I don't know if you've seen the movie Interstellar, but there's a bit where, Matthew McConaughey, the very good looking Matthew McConaughey is probably my favorite male actor. He falls into a black hole. And when he kind of falls into the black hole, he starts seeing things in many dimensions at the same time. He, is able to move back and forward in time, forward and back in space. he goes back to talk to his daughter or whatever, back on Earth, and he's just able to transit around the universe. And so it's portrayed in the movie that he's moving in this like hyperdimensional space or n-dimensional space. And so one of the leading approaches to making a problem that's hard for quantum computers actually harnesses this same idea. We try to build a mathematical problem that operates not just in a single dimensional space, like elliptic curves really operate in a two-dimensional space. Okay, you could draw elliptic curves on a piece of paper. We actually, for example, the lattice-based schemes that we've added to Algorand, and I'll talk about how they secure us in a moment, those lattice-based schemes operate in n-dimensional space. We have hundreds of dimensions or thousands of dimensions that these lattices operate in. You can't even visualize this stuff because we only understand 3D, maybe some of us 4D. When you start to get hundreds of dimensions, I mean, what does that even mean? It looks like Interstellar. And so we use these kind of n-dimensional mathematical structures in order to make problems that are even hard for something like a quantum computer that operates with massive parallelism. And so, yeah, to answer your question, Algorand is kind of 1/3 of the journey here. It's like 33% of the way. Now, let me tell you, I see a lot of things said about blockchains, whether they're AI tokens and AI blockchains, and then I see others that call themselves quantum secure. You want to be checking that because there's so much spoof out there. This stuff is like bleeding edge math. There's like about 100 people on Earth who understand it properly, even less that can implement it. And so a lot of these kind of quantum-proof blockchains are just bullshit. But we genuinely at Algorand, we have some of these folks on staff, people who've invented this math. Chris Picart is one. He works at Algorand Technologies. And we have used a technology known as Falcon, which harnesses these n-dimensional lattices from Interstellar that I just talked about to secure the history of the blockchain. So every 256 rounds, i.e. every 256 blocks, we cryptographically sign with a post-quantum digital signature that quantum computers cannot break the 256 blocks. And then we wait for the next 256 and then we sign them. And so we are essentially protecting in batches of 256 blocks the entire history of the chain. Now, that affords us great security. It's not perfect, and I'll come to where we need to change other parts. But it does allow us to sit back and say, well, if a transaction was done 10 minutes ago or 12 minutes ago, it's quantum secure. And that's a powerful statement.
Wow.
Now, we still have to... Sorry, yeah, tell me.
It seems to me that is the most important thing, right? I mean, the other two components, securing accounts and securing consensus, the fact that these are not quantum secure today isn't really a problem because there's no quantum computers out there that could potentially break these, right? And
well,
so
yes.
it seems to me that the most important thing we can do as a blockchain is making sure that the history is secure so that in 5 or 10 years from now or 20 years from now, whenever a quantum computer is actually reality, that then we make sure that all the historical transactions cannot be broken. So it seems to me that is the right approach. Today, there's no quantum computers, so we don't have to solve a problem that does not exist. But we do have to make sure that when in the future a quantum computer is there, that they can break the history of the blockchain. So that feels to me like the most important thing to get right.
I would say it's primary for sure, because I would rather a world where we draw a line in the sand and say, well, quantum computers just emerged, we have a problem and we're going to have to fix it. And I know all of my balances and everything I've done thus far is secure. I'd rather that than, for example, to be secure going forward, but not to have security in the history. But still, of course, we do need to move to a post-quantum VRF, probably based on lattices. We do need to move to a post-quantum signature scheme so that, as Min said earlier, Min made an interesting point. On the Ethereum side, they make a statement that if you make a transaction, your public key has to be part of the transaction for it to be verified. And once they have your public key, you can run shores on the public key, get the private key, and then spend the funds. That's the whole idea there. And so we do also need to take care of that. We do need to be in a place that if there is active quantum computers out there, sure, the history is good, but so is the next block in the chain, so is the transaction I just sent. Yeah. But you're absolutely right, Marc. I do think that you're right. It's more important to secure the history.
What does it mean to make the signature schemes quantum resistant and to make VRF quantum resistant? Like what's the work that's involved? Is it kind of building upon the work that we did to secure the history, or is it new stuff that has to be built?
In the case of consensus and the VRF, it's new stuff. So the current VRF, very quickly, is essentially an asymmetric HMAC function predicated upon ED25519 or Edwards 25519 elliptic curve, and that's not quantum secure. So we'll have to move to a VRF that is based upon a different structure. But then for accounts, it's a little bit more nuanced. The public keys and private keys for post-quantum schemes are different sizes to those that we use with elliptic curves. And so you know how you write down your 24 words? That's great. You know how many words you'd be writing down for a post-quantum key? About 700 or 800. And so it's a bigger private key. And so we have to figure that out. We haven't really figured out exactly how that's going to work. There are ways we can do it using account abstraction. For example, we could have logic SIGs that do not decode to a point within a curve and have a Falcon verify inside them. And so we're thinking about how we can do this, but we're not there yet.
And so if you look at the how we secure the history, we use a uniquely Algorand feature, the state proofs, right?
Yeah.
And how does that work? Is that so? You said something about 256 blocks. So for the history to be secure, my understanding is it would take 256 blocks because that's when state proofs happen.
Right. Well, they're on a set cadence, so it depends on where you fall. If you make your transaction early in the cycle, if you like, you have to wait 256 blocks. But if you're just 5 blocks before the one's just stamped, then you're probably good in you're obviously good in just 5 blocks. So it depends. So at most about 12 minutes at our current block time. At least about 6 seconds for your quantum security. How does that work? Yes, we use state proofs. What are they? They're essentially a succinct proof of the blocks and the transactions within the blocks, and not yet the metadata actually, but for soon the metadata too. And those structures are then signed with Falcon and NIST approved, so government approved post-quantum signature scheme based on lattices, as I described before. And so, yeah, that's essentially how we gain quantum security. We use Falcon. It is I was going to say bulletproof. We can't say bulletproof just yet because many times cryptographic primitives or structures exist for 10, 20, 30 years and then are broken. And I'd just like to highlight one thing. Very recently, there was a paper by a gentleman called Chen, which purported to find a polynomial time solution to learning with errors and lattice-based problems in a quantum context. And what this meant was quantum computers might actually be able to break these lattice things I talked about. And of course, that would break state proofs and other things. It turned out, though, that there was a bug in his paper and actually lattices were still safe. But the reason I highlight this is not to scare anyone, but just to say, we think Falcon is great. So does the US government. And so far, the scientific community hasn't been able to find a problem with it. But you never know. And there's new technologies and mathematics that emerge every day. And so, we should just like classical computing, maybe classical cryptography may be broken someday. We should always be watching what's happening and ready to react and improve the security of the blockchain whenever needed.
Yeah, I think it's probably worth highlighting. And again, this is something that it's more your field, John, and much more technical. But Falcon is one of 4 standards, right, that NIST has sort of whittled down out of more than 80 to say that after years of looking into it and the research to indicate that it is one of the most secure and one of the standards that we should be adopting as a whole in the industry. So I think that just shows the level of credibility and the level of scrutiny this technology has gone through. So I think that is kind of, although I think Algorand was ahead of its time. In fact, right, we used Falcon before NIST had even indicated that this is one of the finalists.
Yeah, we had an advantage in the sense that some of our people co-invented this stuff, so it's easier. It's easier when you're part of the people who invented it. By the way, NIST, for those who are maybe not as technical, is a U.S. institute. I think it's the National Institute for Standards and Tech. Is that right?
Yes. Yeah, that's exactly right. And the
so
simplest thing is it's like it's part of the Department of Commerce. Not part of NSA or any of the defense, but it's actually about part of Department of Commerce.
Right. I think again, I'm not an American citizen, so what do I know? But I think that their job is to standardize things in an objective way, right?
Yeah, and they set the standard for like all the previous standards for the internet and all that stuff too. Yeah, yes. Exactly.
Including, by the way, the dual deterministic random bit generator that the NSA had backdoored. So just be careful of that.
Different departments. Right?
Different departments.
Like I said.
So yeah, I think it's a very exciting area of technology, and I'm glad we're addressing it now. I mean, it used to be kind of science fiction, but I think it's becoming much more real.
Is anyone else doing sort of, what I think we should call it, Algorand, is quantum forward. We're looking ahead. Is anyone else being quantum forward?
I would even call us a quantum leader. I mean,
Quantum, yeah.
of course, I don't know all projects, right? But I genuinely have not seen a single other project that has credible quantum security yet. And so if you do have that project, please tell me in the comments, not just the name of the project, but also what it's using in order to achieve that and how it's been technically implemented, because I have not seen any other blockchains out there, including the big ones like Cardano, Bitcoin, and Ethereum. None of them, or Solana, none of them have any quantum security yet.
I mean, I think what's interesting to me as well is that, I mean, as you know, Algorand is like, we focus really Algorand on real world use cases at scale. And this quantum challenge, I don't think is a theoretical challenge for, if you think about use cases that involve large institutions, governments, treasuries, and those types of use cases. Those people typically have a much longer time frame than your regular app developer out there. And so if you're thinking about like tokenizing treasuries or tokenizing those types of assets, they will live for a long time. And so I think the idea of having the chain be quantum secure from a history perspective is actually not a theoretical, thing. It's a real thing that institutions do care about and do want to make sure is covered. And I think it positions us in a very unique way as the only blockchain who can actually deliver on that promise. And I think that's quite important, specifically in that context.
Right. And going back to Silvio's speech at Paris Blockchain Week, he identified the same thing, which is that governments and major institutions, they want post quantum security. You only have to look at iMessage, Apple's messaging platform, the blue bubbles. You only have to look at Signal. You only have to look at Google Chrome, which has added Kyber and other post-quantum primitives there too for key encapsulation. And so, we are absolutely seeing these major orgs and major trillion-dollar companies move to a post-quantum tech stack. And I think certainly, if we're going to be the future of money and the future of decentralized finance, we need to do that too. And I'm glad we're on that journey.
Yeah, I mean, I think most large corporations are absolutely thinking about this. I think I read somewhere that Cloudflare said, currently they have about 2% of their traffic is established using post-quantum cryptography. But by the end of the year, they expect it to be in double digits, right? Like, I think the trajectory of all these different organizations making sure that they are quantum resistant is going to pick up exponentially. So to your point, Marc, it's a great place for us to be ahead of that curve. But also, John, I think your other point being there's a lot more work for us to be done to secure the other two legs of that stool.
It's very interesting though, man. I hadn't realized, like, I wouldn't have thought it was anything like that, but wow, 2%. I mean, I know that doesn't sound like a ton, but like that's a lot.
That's a lot. And they expect double digits by the end of the year, which means that it's not just, it's going to grow and it's going to be everybody. It's an ecosystem, because for Cloudflare, it means it's the end user apps and it's the infrastructure folks too. So
yeah, it's super cool. I think it's really, really interesting. And like I said, we will do the accounts. We will eventually do the VRF, but we want to make sure whatever we roll out is really, really, really robust. Ultimately, to do the accounts, we have to make sure that we give a good user experience. It can't just be that we transit to something that's post-quantum, but then you've got to write down 2 pages worth of words in order to back up your key, right? So these are the kind of user experience issues that we have to make sure we meet whilst we're also solving the technical security issues.
John, can I ask a question about this 256 blocks? Is that absolutely something that we set? Sorry?
I said fingers crossed like an answer.
Oh, it'll be, this is going to be a baby one for you. No, but is that something that we set to kind of like optimize the computational, I don't know what the right word is, the computational burden, right, for this? Like, is that something that can change in the future? Will we be able to shorten the amount of time and the number of blocks every time that it gets secured?
Very much so. And so 256 was selected as a balance. A state proof is about 4 megabytes in size. So that's not enormous, but it's sizable enough. It's like, an MP3 from 1990. And so we write one of them to the chain every 12 minutes. We could make it 128 blocks. We could make it 64 blocks. We could make it 32 blocks. It's a matter of, as you just said, what is the computational burden of the stake having to create the proof, sign the proof using Falcon, which is this lattice thing, which takes a couple of seconds to sign, or a few 100 milliseconds, and then adding that state proof to the chain takes some space. And so we're just trying to balance all those things. But fundamentally, 100%, we could shorten it or elongate it if we needed to.
And so were state proofs specifically created for this quantum security, or were there other use cases as well to state proofs?
Well, that's a very interesting question, Marc. The reality is state proofs were actually created with interoperability in mind. And so state proofs are a succinct, i.e. small, 4 megabyte, proof of all the transactions that have occurred in the last 256 blocks. Now, let me just see what that is. That's going to be 256 blocks multiplied by, let's say, blocks every 3 seconds. So you'd expect, if we're doing 10,000 transactions a second, it's 30,000 transactions in 3 seconds. So like you do 30,000 there. So that might be like 7.5 million transactions or so. So we have 4 megabytes proving the state of 7.5 million transactions. Mm-hmm. And so that's a very powerful thing. And this is important if we want to make a trustless bridge to like Cardano. Wouldn't it be great if we could just say to Cardano as a protocol, here is a little bit of data that you can use to verify 7.5 million transactions over here without having to look through them. And that was the original idea of state proofs. How can we succinctly prove? But it turned out that the folks, the tech guys, essentially thought, oh, it'd be great if we signed these state proofs with something that also added quantum security. I mean, why not? It's a nice place for that to slot in, and that's where Falcon was chosen.
That's super cool. 7.3 million transactions in one 4 megabyte proof.
I hope that maths is right, but I think that's right.
I know. Yeah. We got to double check it.
Look it up on my quantum computer.
Yeah.
Exactly. That's awesome. Hey guys, what do you guys think? I think this is maybe a good time to pull in our core ecosystem correspondent to give us a little bit of an update.
Well, I've got a question. Will he be well dressed today? I mean, he was very well dressed the last time.
I mean, do you expect anything less? Let's see. Okay. Can't keep the suspense anymore. Let's do it. Fred Estante, can you please come share with us what's been going on in the ecosystem? And look at him.
Fred.
Here I am.
Fred, I felt really underdressed the last time you were here, so I decided to dress up today. So I wore a shirt, which I typically don't do, specifically for you.
Fantastic. Thank you, Marc. I'm very happy that at least you took the memo seriously today. So I appreciate it.
But I still can't compete. Like the tie and the jacket, that I can't compete. I can't compete.
It's an Algorand tie.
I try it.
Right. But it's an Algorand tie. It's pretty unique. But hey, maybe I can get you one by Decipher. We'll see. Okay. Fantastic. Well, me, John, Marc, thank you very much, for inviting me again. I'm thrilled to be back. Very pumped to be here and share with the community a lot of ecosystem updates that happened in the last few weeks, since the last episode. So yeah, I'm ready to jump right in. Let's do it. All right. So last time I started, with information about, the infrastructure vertical. So to mix things up a little bit, this time I'm actually going to start with XGov. Okay. So first of all, the XGov voting session number 4 is now live. There are currently 22 proposals that you can vote for in the current period. Of course, if you're a registered XGov, and you should all be, right? Last I checked, 6 proposals had already passed, but only around 50% of the stake had already voted, which means there's still time and voting power for many other proposals to be approved by the community. The voting session closes on June 3rd, so hurry up. But you still got about 2 weeks or so. But hurry up, don't waste any time. So far, the 6 proposals that have already passed are the Cometa Launchpad, which is basically to launch a service to facilitate token launches on Algorand. Trails scam detector and real-world asset tokenization insights. So they upped their own dashboard for this. The scam bot transaction fee refunds by the one and only D13. We also passed the TealScript interactive developer course by Ethan Klein, the open source no-code tools developed by the amazing team from Thirstover, and the Cosmic Champs retroactive funding for their play-to-earn game that is gaining a lot of traction in our ecosystem. And just, still on the XGov topic, just before we wrap up and move on, just a call to the Algo fam. Visit the Algorand forum, okay? That is the place where all the discussions are happening. There are currently dozens and dozens of open threads of people discussing, all sorts of proposals, TDR plans from DeFi protocols, NFT rewards, and bunch of other random things which are pretty cool to follow. A lot of crazy science and DeFi and stuff being discussed. So I highly recommend check out the Algorand forum. That is where the action happens. Twitter's pretty cool. Reddit's awesome. Algorand forum is the place to be, right? So make sure to check it out. But okay, cool. I'm done with XGOS for today. Let's jump into DeFi. I'll start with, I think, one of the updates that got me the most excited in the last 2 weeks, which is DEX Screener. The integration with DEX Screener is now live on Algorand. So now the entire crypto community, all over the world, can head out to DEX Screener and discover real-time stats from Algorand DeFi. Tinyman is already integrated, and other AMMs are also, looking to integrate. So DeFi builders that are listening to this podcast, take this seriously, okay? Integrate your dApps. Let's show the world the power of Algorand DeFi. And on this topic, I just want to say, a huge shout out and thank you to Barb and Tinyman for leading this initiative. This shows the power of the community. You guys can make a difference. You took this in your own hands and you were able to get this done. So congratulations, huge kudos to you both. Thanks for doing this and keep doing it. All right. And well, still talking about Tinyman, just to make sure that it's covered, that Tinyman was announced as one of the sponsors for the DeFi track of the Algorand Global Hackathon. So they're very involved in the ongoing hackathon that we have right now. Messina is hosting the second version of the tokens tournament. There's a lot of action happening there. So make sure to check it out and vote which Algorand token you believe has the most cross-chain potential, and then Messina is going to add it to their bridge. Folks Finance is also sponsoring the DeFi track in the Algorand Global Hackathon, and they also just recently integrated the Loot wallet. Cometa released a bunch of things recently. So they released a UI update to fix some state filtering, for the state of pools and everything else. They also launched a betting system for the Meta Battles game they have, and they also worked with Messina to bridge the DGen token to Algorand. These guys are pretty busy, so guys, keep doing the great work. Keep at it. Compex acquired XBECT, to increase the their DeFi product lineup, and ParaWallet dropped the swap fees entirely. Some great stuff happening in DeFi. But let's move on. Let's talk a little bit about real-world assets here. Lofty, of course, continues to tokenize new properties and deploy new liquidity pools against these properties like there's no tomorrow. I just spoke to Jeremy, and he mentioned to me that so far they have already tokenized over 170 properties, with about 120 of those currently available in the platform. Out of this, dozens of them already have liquidity pools against them with a total TVL of $1.3 million against all, several of these properties. Land Token, a tokenization project out of Argentina, just tokenized another land farm in the region. The latest one is called Dom Pedro, and it has 348 acres of productive land that has just been tokenized and on Algorand. Coinbanks attended the FinTech Americas conference in Miami, and Leo, their CEO, moderated a panel on innovative payments and tokenization. Coinbanks also recently gave a great presentation on the UNDP, the United Nations Development Program Algorand Blockchain Academy, and they also attended and spoke at the PayTech conference in Colombia, one of the region's most important payments conference. A-Note released several new royalty payouts from some of their music catalogs to their users. And AgroToken was also present at AgroConnect, which is a great relevant conference here in the region. And Ariel, their CTO, spoke at the event about the tokenization of agro commodities. And of course, that's all leveraging the Algorand blockchain. Moving on, NFTs and gaming. Also a lot of stuff happening there. Fractal Labs just released, treasure hunts. So that's a whole new way, and really fun way to play the game and earn some NFTs and earn some new rewards. And the cool thing about Fractal Labs is that they tied this, very closely to another update they just released, a few days before, which brings a great onboarding experience, to bring new users to Algorand, users from other blockchains, or even users are just Web2 gamers, that it's really easy to onboard them and also gives them NFTs and assets they can use in the game. So, pretty cool initiative that the team is doing. So nice job, guys. Realms, they finally released the website and it looks absolutely incredible. They have also been dropping many cross-chain partnerships with NFT projects in many different blockchains ahead of the launch of their virtual world. So again, I'm very excited for this and I'm looking forward to the next releases they're gonna give us. AlgoX NFT continues to deliver quality of life updates every single week. They just released new parts of the website with a whole new and improved UI and UX. They also released a better way to manage your shuffles, collections, liking NFTs, etc. A lot of new functionality. These guys really don't stop. And the next one, it's something that I'm personally very excited about because I'm a nerd, and I know John loves this as well, and he's already smiling. I think he knows what I'm going to talk about. Is that the good folks from Data History Museum, they just announced on Twitter, and I can take blame/credit for this because I bugged them so much on Twitter that they finally let it slide, that they're creating a store for all these amazing assets that have been minting on chain since 2022. So, in the last 2 years, every time there's an earthquake or a solar flare that happens on Earth or on the sun, they automatically generate an NFT that has information about this event. And all of this is an Algorand, so after many years of myself, of course, many others bugging them, they're creating a store to allow, you, me, and many others to bid on these things and, own a piece of, nature history, right? So you can own the data affiliated with an earthquake or solar flare, etc. So I'm very, very excited about this. And at last for NFTs, but certainly not least, we just announced the call for creators ahead of Decipher. So Diagram Nation we just announced this call, which is really like a really amazing activation to rally the community, our entire ecosystem for Decipher. So artists from our community, if you're listening to this now, you're all invited to submit your artwork, and then the community will vote which are, the top 10 favorite NFTs that are created by you. And then this top 10, which are voted by the community, are going to be awarded 5,000 algos each. So it's a grand total, prize of 50,000 algos. So if you're an artist in our community, in our ecosystem, go ahead, submit your NFT because the community will choose their favorites. And this is going to be featured both in the Algorand, NFT collection, but it's also going to be featured in the NFT exhibit in Decipher. Okay, so do this. All right, moving on. Infrastructure and access. A lot of stuff happening there as well. So Protofire just launched a public API endpoint for Algorand. So it's just another great option for for the builders in our ecosystem to experiment and use them as an infra provider, or at least adopt them as a secondary provider, as a backup for your dApps. Coinstore, an Asia-based crypto exchange, just added support for USDC on Algorand. So we continue to expand the reach of stablecoins, mainly USDC, through Algorand all over the world. Our friend from Go Plausible just released another 2 amazing upgrades. One of them is token gatekeeping. So you can now use tokens ASAs as gatekeepers to only allow a specific wallet to claim the Plus assets whenever you're doing claims for an event or something that you're doing. And they also released functionality to basically stop double claiming from drops. Kudos to MG and the team to really great quality of life upgrades for the end users, but also for the ones that are using the Plus to distribute in their events. Julio launched Algo Plonk, a tool to allow builders to create zero-knowledge applications on Algorand. And I see John clapping there, so I think John is pretty excited about this. Maybe you can explain, to us normies afterwards what all of this means, John. But they just did it, and it sounds like a really big deal. All right. Gora Network, they recently released the ERC20 version of the token, but it is native to Algorand like it has always been. And they also just released a Galaxy test campaign, right? And so, for all the community out there, there's a bunch of initiatives you can do to get more involved with Gora. And they're also, of course, sponsoring the interoperability track in the Algorand Global Hackathon alongside with Wormhole. Chaintrail, like those guys don't stop as well. They just released a lot of UI updates. It looks fast. It feels faster and looks slicker than ever. Check it out. One of the best ways to find out everything about statistics and analytics on Algorand. They look at every single corner. Fantastic product. Loot Wallet has just integrated with Stasis Euro token, so it's now also available in their wallet. Para Explorer added a bunch of new functionality recently. The ones that I want to bring attention to are basically that the Para Explorer now shows the burned amount, for non-clawback assets. And they also just released the celebratory NFTs for Governance Period 10. So if you were governed in GP10, just head out to Para's website and claim your free NFT, that states that you are an Algorand governor, okay? Do that. Ripple and XRP Labs have joined our DREC, the Decentralized Recovery Alliance. More power to cross-chain initiatives that already has, Hedera, Casper, and many other protocols involved in. Maybe John will give us an update at some point in the next couple of weeks about this, but certainly a big deal. Blockstalker released an update to the protocol, and now it has basically pause and resume functionality for data streams and event-driven alerts. And talking about explorers large and data, there's a new explorer in the block. And I really hope you picked up on the pun that I did that. It was on purpose, okay? So welcome to the ecosystem block pack, a new block explorer developed by Shiva, prominent builder in our ecosystem. So welcome to our ecosystem. And at last but certainly not least, Nodally, formerly AlgoNode, have just removed the request quotas and also added just a free cloud VM for all XGov and open source public goods projects in Algorand. So if you're either an XGov builder or you're doing something open source as a public good for the ecosystem, AlgoNode's there to help you even more. They have already helped you, all of us a lot in the past, but this guy just keeps pushing the boundaries. So huge kudos to Ortho and the team for doing this incredible stuff. And I'm done, I think, with the major teams, the major verticals that I wanted to share today. But actually, there are two more things that I want to talk very quickly. One of them is actually I want to do something different and give two honorable mentions or two big shout outs for things that don't really fit into any of this, the balloons and all. It doesn't really fit into any of these categories, but I think these things are pretty cool. Okay. So shout out number one is to my friend and colleague, Matt Keller, our head of impact here at the Algorand Foundation. Matt just represented Algorand and AidTech at the NVC 2024 conference, and there, he showcased the Care Survival Wallet, which is another fantastic real-world impact project, which of course is built on Algorand Rails. And the second shout out that I want to do today is to the one and only Carlos Lima from Portugal, who recently, just a few weeks ago, launched a high altitude balloon, with his students that went, all the way to the edge of space. And that's pretty cool by itself because, it's bringing awareness about, STEM and sciences to everybody. But the really cool thing about this is, of course, the balloon, which is doing a lot of fun stuff and fun science and telemetry and sending data back down to Earth, had an Algorand node to it, So you can say that Algorand has flown into the edge of space. That was pretty spectacular. Carlos, congratulations to you, all of your students, the team, everybody involved. Fantastic initiative. And I'm looking forward to the next launch, okay? And before I wrap up, there's just one last thing that I want to share today, which are stats. So just a very quick summary of some of the cool things that happened in Algorand, in the last couple of weeks. So basically, in the last 30 days, the Algorand protocol processed a little over 900,000 blocks, right? So it's 902,000 blocks, which processed, within these blocks, we processed over 99.2 million transactions. So we nearly cracked 100 million transactions in the last 30 days, with an average block time of 2.87 seconds and an average TPS, our transactional throughput, of 110 transactions per second. And this info is, of course, brought to you by the one and only, Algorand mainnet dashboard powered by Nodally. So once again, kudos to Ortho, Pavel and his team for, giving us all this amazing data in this dashboard, which of course has a lot more stuff. I just covered the very basics here. So team, I think that's all that I had for today. Wow. Thank you very much for having me.
It's like so much stuff. It's unbelievable. I think we're going to have to extend the runtime of this podcast to be able, to have you cover everything that's going on. It's so exciting.
Yeah, if you can give me about 5 hours, I think that should do it, Marc.
Yeah.
Yeah, and we'll share that.
I can't imagine with like the influx of new Python developers that followed our bootcamp and are now participating in a hackathon. I mean, it's only going to get better and better as we go forward, right?
Just to build on that one, by the way, Fred, you're unbelievable the way you do this stuff. So much more work goes into what Fred just did than me waffling about quantum computers. So Fred, you really are a star. But I just want to touch on one of the things. You mentioned loads of great stuff, but I want to give a shout out to Giulio, who built AlgoPlonk. I want to talk about that for a second because it's so technical. I think people have missed it, and I'm super excited about it. So, and it was another product of Python. So this would not have been possible with Python because it's just too complicated to build with Teal. You couldn't do it. It would take years. And so Giulio built this because he had Python and he was able to implement it. And so what AlgoPlonk is, Algorand, Plonk is a very popular zero knowledge proving system, or a way to express ZK circuits. And so what he's done is he's created a toy box for zero knowledge proofs on Algorand. So if you want to build a zero knowledge proof on Algorand, and you can do so many things. You can do private transactions. You can, for example, prove that you own a specific thing without revealing the information. So anything you can do with a zero knowledge proof, you can now do using AlgoPlonk on Algorand. And it's, like I said, it's a toolbox or a toy box full of Lego bricks that you can quickly build ZK circuits with. And so using his technology in a few lines of code, you can export an Algorand smart contract that's been written in Python and then later on compiled to AVM bytecode and deploy your zero knowledge application. So it's like a framework for building zero knowledge applications. And again, just came out of nowhere, just someone from the community, another smart person from the community, just building something wonderful. And again, a side effect of technologies like Python, which enable people like Giulio to build incredible things. So I'm just, I was so blown away by it. It's super cool.
Awesome. Thanks, John. Thanks for having me. It was a pleasure being back here. See you next time.
Fred, thank you so much. This is the best. All right, guys. I was thinking we should wrap up with a little bit of a prediction into the future. When do you guys think quantum computing is going to arrive? So why don't we start with Marc?
I think I would guess it's going to be at least 10 years.
10 years. So 2034.
Yeah.
I'm doing some good math here for us. How about you, John? What do you think?
I think before 2030. I think we're on the knee of the curve. I mean, I don't think it's like imminent, but I think it's before 2030. I would say predictions always make people look silly, but yeah, I'll say before 2030. I even think as early as like 2028, 2029, we'll see something that, what does it mean, by the way, to see quantum computers? What I'm talking about is something that breaks meaningful cryptography. Yeah. What is that for me? Let's say like RSA, 1024, like 128-bit RSA. If that can be broken, that is meaningful. And so I think before 2030 for something like that.
But 128 is what most of the internet uses right now, right? Or that is the one that we should be sort of thinking about, isn't it?
Right. And RSA is funny because like it's the key is like 2048-bit or 4096-bit, but it translates to 128-bit security, 112-bit security, that kind of thing, because of the way RSA works. But yeah, I guess breaking asymmetric cryptography with a bit strength that's 128 or higher. If that happens, I think that is where we then have to rely upon 256-bit schemes. I think that will be a watershed moment, and I think before 2030. Yeah.
2030, before 2030. So now, Marc, you can readjust your answer if you like, because John just kind of classified it a little bit.
Into my guns.
Yeah.
10 years. 10 years.
I like it. I like it.
How about you?
Min? Tell me. What do you?
I'm closer to the 10 year than I am to the 2030. I think it's just, it feels so far away. But I know that's just maybe me being optimistic here. So I'm actually on the 10-year camp. I think 2034. Call it 2035. I'm even beyond Marc.
Let's make it interesting then. Let's make it interesting. Let's put some algo bets on. What can we do here? Maybe let's say 500 algo. I will pay each of you 500 algo. The day how can I structure this in kind of a leveraged way? For every day after 2030 that quantum computers do not emerge, I will send you 10 algo. But for every day before 2030, I want you to give me a multiple of 500 algo. Will you take this bet?
My algo address is markvl.algo. Please keep
that's confidence. That is confidence.
Yeah. That's awesome. All right, cool. I guess we'll have to do this podcast at least until 2034 to know whether or not quantum computing is going to be here.
Right. Exactly.
Right?
Exactly.
All right. With that, I guess, everyone, thank you so much for joining us, and we will see you again in 2 weeks.
Thank you. Bye.
Bye, everyone.